Okay, guys, welcome. Today we're going to talk about the normal distribution. Now, the normal distribution is a special and very common type of distribution, so we're going to talk about it extensively in this section. And it's represented by a bell-shaped curve, and we formally call this the normal distribution. Right, so the normal distribution is symmetric and it's bell-shaped with a single peak. Now, its peak, of course, since it's symmetric, is represents the mean, median, and mode of the distribution. Now we talk about the variation described by the normal distribution by using its standard deviation. Now, this figure in the textbook, which I've sort of copied down here, shows two distributions. In this first one, we have a famous data set of the chest sizes of 5,738 Scottish militiamen collected in about 1846. And in part B, we have the distribution of the population densities of the 50 states. Now, is either distribution a normal distribution? And of course, by looking at these two, you can see that this one is normal, right? Why is it normal? Well, it's symmetric about the mean. It's bell-shaped. And if you wanted to, you could characterize it by its standard deviation. Now, this one, of course, is not normal. And it is, in fact, right skewed. Right? Because if you were to fit a distribution over it, it would probably look something like this. Right? Whereas this one would look how we would want it to look. It would look like the normal distribution. All right, so that's the idea there. Now, what are some examples of common normal distributions? Things like heights, SAT scores, batting averages, salaries at a company are all good examples of normal distributions. It's where you can expect most data values to be centered around the mean, with it symmetric, of course, and then decreasing in frequency as you get further away from the mean. So now, what are some conditions that promote a normal distribution? Okay. Now, a data set that satisfies the following four criteria is likely to have a nearly normal or normal distribution. So the first characteristic is that most data values are clustered near the mean, giving the distribution a well-defined peak. Then the next thing, of course, is that data values are spread evenly around the mean, and that makes the distribution symmetric. And of course, larger deviations from the mean become increasingly rare, and that gives you the tails on either end of the distribution. And of course, one thing that allows this sort of thing to happen is that the individual data values result from a combination of many different factors, such as genetic and environmental factors. Now, for the next example, we want to talk about, well, which of the following variables will we expect to have a normal or nearly normal distribution? Now, scores on a very easy test, we would not expect to be normal, because you would expect most people to do well. And it would not be symmetric, right? You'd probably get something like this, because most people would do well. Now, for part B, shoe sizes of a random sample of adult women, this probably would be normal, because you'd expect that most people would be around the mean and median and mode of the distribution, and then as you get further from that average, it becomes less and less common. Now, a special rule exists for the guidelines for the percentage of data values that lie within 1, 2, and 3 standard deviations of the mean for any normal distribution, and this is called the 68, 95, 99.7 rule. And here's what we mean by this. So let me go ahead, and I wonder if I can make this picture bigger. It doesn't look like I can, but let me draw it out here. Okay, so if we have a normal distribution, we have something like that. Now, of course, in the middle is where you have your mean. And of course, the median and the mode, but I'm just going to say the mean. Now, if you go one standard deviation away, So we'll say this is +1 standard deviation, and this is -1 standard deviation. Okay, now the first part of the 68, 95, 99.7 rule says that about 68% of the data points fall within 1 standard deviation of the mean. So if you look in this section, you're going to find 68% of all of your data values in there. They're going to be between 1 standard deviation below and 1 standard deviation above the mean. Now, if you go out to 2 standard deviations, right, and let me see, let's erase this one. And we're now talking about this region. So everything in the middle, 68, but now also this. In that green part, you're going to have 95% of the data points. Now, if you go out to 1 more deviation, so now you're looking at everything in between these 3. I should get rid of this 68 too. Now, if you look at all of this, so everything in between these 2, so we're looking at all this stuff. In this region, you now have 99.7% of the data points. So only 0.3% would be outside of this region. Okay, so that's what we mean by the 68, 95, 99.7 rule. Okay, so in this next example, we have that each test that makes up the verbal and mathematics part of the SAT is designed so its scores are normally distributed with a mean of 500 and a standard deviation of 100. Okay, so we'll interpret this statement according to the 68, 95, 99.7 rule. So basically what we want to do, or at least what I will do for this demonstration, is we'll show what this looks like. Well, we know that the mean is 500, so that's going to be here. Now, if its standard deviation is 100, then 1 standard deviation above would be 600. 2 standard deviations above would be 700. And 3 would be 800. Right? Then we can also go the other way, and we would have 400, 300, and 200. So if we interpret this, well, the 68 part applies for 1 standard deviation. So 68% of the scores are between 400 and 600. Because that's +1 and -1 standard deviation from the mean. Then if we look at 95%, that's out an additional 1 standard deviation, so 95% of scores are between 300 and 700. Okay, and then finally, 99.7% would give us at 99.7% of scores are between 200 and 800. So that's what we mean by the 68, 95, 99.7 rule. So if we know that a distribution is normal, then we can say these things about our data sets. Okay, now in this next example, we have that vending machines can be adjusted to reject coins above and below certain weights. Now, the weights of legal US quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.07 grams. Now, if we have that a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? Well, again, since we have a normal distribution and we're looking at percentages, we want to use our 68, 95, 99.7 rule. Okay, so the mean is 5.67. And since the standard deviation is 0.07, if I go up 1, that will be 5.74. If I go up 1 more, I'll get the 5.81. So we see that that's 2 standard deviations away. And if we go in the other direction, we're going to have a 5.6 and a 5.53, which is also 2 standard deviations. Now, since this is 2 standard deviations, we know that in here, we have 95% of the data by the 68, 95, 99.7 rule. So what percentage of legal quarters will be rejected by the machine? Well, that's everything else. So that's 100 minus 95%, which of course would give us 5% of legal quarters would get rejected. Okay, so that's another application of the 68, 95, 99.7 rule. Okay, so in this next example, we have that a survey finds that prices paid for 2-year-old Ford Fusion cars are normally distributed with a mean of 17,500 and a standard deviation of 500. So we'll consider a sample of 10,000 people who bought 2-year-old Ford Fusions. So now we want to answer these questions about how many people paid between each of these amounts. Okay, so again, let's go ahead and let's draw our normal distribution. We'll fill everything in here. So we have that our mean is 17,500 and our standard deviation is 500. So if I go up here, I have 18,000 and I have 18,500 and then 19,000. So that would be 3 standard deviations. And then we have 17,000, 16,500, and 16 would give us 3 standard deviations in each direction. Now, how many people for part A paid between 17,000 and 1,800? Well, that's this region where we have 1 standard deviation, so that's 68%. And since it's a sample of 10,000 people, so we want 68% of 10,000, which would give us 6,800. Right? If we multiply 0.68 by 10,000, we would get 6,800 or 6,800. Okay. Now, on the next one, we want to know how many people paid less than 17,000. So now we want, oops. So now we want, for paying less than 17,000, we want this region right here, right? Well, now we have to be a little bit clever because we know that there was 68% in the middle, which leaves us 32% for both sides. Right? Would be both of these added together. And since I only want half of it, we would get that 16% of 10,000. Because I just want the lower part. And since it's symmetric, I'm allowed to cut it in half. So then that would give me a 1,600. And then to get how many people paid more than 19,000 is sort of similar, only now we know that between this, and of course everything in the middle, we know that there's 99.7%. So sort of by the same argument, we know that in this part, we have the leftover part, which is 0.3%. And since I just want 1/2 of it, that's 0.15% of 10,000. Right, and of course, if I do that, I would take, so I need to take 0.15 and move the decimal place over again. So you got to be careful, and then multiply that by 10,000, and you would only get 15 in this case. All right, so that's the idea. So another application of this 68, 95, 99.7 rule. Now, the last thing that we'll talk about in this video is the idea of what we mean by standard scores. Now, standardizing normal distribution data points is common because we can just then talk about data points by classifying them with the number of standard deviations from the mean that they are. Now, the number of standard deviations a data value lies above or below the mean is what we call a standard score or a z-score. Now, a standard score of the mean is 0 because it's 0 standard deviations from the mean, right? If you have a standard score that's 1.5 standard deviations above the mean, then it's positive 1.5. And if it's 2 standard deviations below the mean, we would say that that z-score is -2. So the way that we calculate a z-score or a standard score is you would take that data value, subtract the mean, and then divide that by the standard deviation, right? And of course, it's positive for data values above the mean and negative for data values below the mean. So let's do a couple examples where we calculate a standard score. So in this example, we have the Stanford Binet IQ test is scaled so that scores are normally distributed with a mean of 100 and a standard deviation of 16. We want to find the standard scores for IQ scores of 85, 100, and 125. Now remember, we find the z-score by taking the data value, subtracting the mean, and then divide by the standard deviation. Right? So for example, let's do the 85 first. So if we calculate this for 85, well, it's 85 minus the mean, which is 100, divided by the standard deviation, which is 16. So we get a -15 over 16, which usually we express these as a decimal. So if I do 15 divided by 16, I'm going to get a negative 0.9375. So that's my z-score for 85. Now for 100, there's nothing to calculate. But even if you don't believe me, if you plug it into the formula, it's 100 minus 100 over 16, which is 0 over 16, which is z equals 0, right? Which makes sense because if you're the mean, you're 0 deviations from the mean. And then finally, if we do this for 125, I'm doing 125 minus 100 over 16, so I get positive 25 over 16. And if we divide this, we're going to get a positive z is equal to 1.5625. So that's our z-score there. Okay, now once you know the standard score, you can use that standard score to find the percentage of all the data values in a data set that are either less than or equal to it. So everything up to that data point. Now, a lot of times these are called z-score tables. And a lot of calculators have this option too, but if you don't have a calculator available, it's nice to be able to have a z-score table handy. So for example, if you find a z-score of say, I don't know, let's say 2.34. Well, then what you do is you find on the left-hand column the z-score that starts with 2.3. So that would be here. And then we want the second digit to be 4. So that would be this column. So where do they line up? It looks like they line up to 0.9904. So then that would tell you that 99.4% of the scores are at most 2.34. Right? So that's the idea. So let's look at an example of that. So now cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178 and a standard deviation of 41. So we want to know in what percentile is a 20-year-old man with a cholesterol of 190. Okay, so first thing we need to do is find the z-score. Okay, so if we find this z-score, I need to take 190 minus the mean, which is 178, divided by the standard deviation of 41. So then we would get a 12 over 41. And if I do 12 divided by 41, I'm going to get that my z-score here is a 0.2927. So now that we have the z-score, we can then go to our table and we can find where are we going to have the percentile here. So if we go to our table, I need to find 0.2927. So here it looks like we have 0.2, and there's 9. So it looks like we have 61.41% percentile. I shouldn't say percent, it's percentile, right? Which means that 61.41% of the data points are at most 190, right? So that's the idea there. Okay, and in part B, want to know what cholesterol level corresponds to the 90th percentile, the level at which treatment may be necessary. So now we have to sort of work backwards because now we're given the 90th percentile. So that means that we need to look for the z-score that corresponds to 0.90. All right, so let's go to our table and we need to find 0.90. So it looks like we're going to first eclipse 90 at around here. So it looks like my z-score for that is going to start with a 1.2, and then it looks like we have an 8 and a 9. So let's split the difference and we'll call it 8.5. All right, so that's the z-score that corresponds. So z is 1.285. Right, now that's not the cholesterol level, that's the z-score. So now we need to, again, use our formula and work backwards. So we now have 1.285 equals the data value that we need to find minus the mean, which is 178, divided by the standard deviation, which is 16. So now we can solve for the data value by multiplying both sides by 16. And if we do 16 times 1.285, we're going to get a 20.56. And now that's equal to our data value minus 178. So now if I add 178 to both sides, I'm going to get that the cholesterol level would be 20.56 plus 178 once I add it to both sides. And that would give me a 198.56. All right, so close to 199 or 200 would be the 90th percentile. Okay, now I think this is, so this is the last example for this video. We have the heights of American women ages 18 to 24 are normally just distributed with a mean of 65 inches and a standard deviation of 2.5 inches. Now, in order to serve in the U.S. Army, I don't know if this is still true or not, but for this example, we have that women must be between 58 inches and 80 inches tall. So what percentage of women are ineligible to serve based on their height? Well, let's go ahead, and this is going to be another z-score. So we have that, so the mean is 65, and standard deviation is 2.5. Right? So what's the z-score for 58? right? Because what we want to find is if here's our normal distribution, right, and we have our mean here, here's 58 somewhere, and here's 80. We want to find these women that are shorter than 58 inches or taller than 80 inches, and those would be the women that would be ineligible. All right, so let's go ahead and let's find our z-score for 58. Well, that would be 58 minus 65 over 2.5. So this z-score, once we calculate it, would be a negative 7 divided by 2.5. So we get that this z-score is negative 2.8. I shouldn't say approximately. This is actually just equal. Right? And if we do the z-score for 80, I would do 80 minus 65 over 2.5, and that would give me a 15 over 2.5. And I want to say this would give me a 6. Yes. Okay, so let's go ahead and let's find what percentiles we get for each of these z-scores. So first, let's find the z-score for 58 inches, which was negative 2.8. So it looks like negative 2.8, and it's 2.80, so we get a 0.0026. Which is going to correspond to a 0.26%. Right? And again, that is giving us the percentage of women that are shorter than 58 inches. Now, when we look at a z-score of 6, 6 is going to be off the table, right? Because the highest that it goes is 3.49, and 6 is much larger than that, right? So this is going to be basically 100%. However, that's all the women that are less than 80 inches, right? We want the opposite. We want more than 80 inches. So if we do 100 minus 100, right, it's kind of silly, but you're going to get 0. So you're going to have a negligible amount of women that are taller than 80 inches. So it looks like we're just going to get the 0.26% that are shorter than 58 inches. Right, so that's sort of the idea. And just for reference, 80 inches would be, so I guess that would be 6'8". And I don't know too many women that are taller than 6'8". So I guess that's why we're getting such a large z-score there. But that concludes this video on the normal distribution. I hope you enjoyed, and I will see you next time.